Hello, everyone. Welcome to the restart of our international online seminar on interval methods and control engineering. And today we will have a presentation, the first presentation after the restart by Lucas Larbi. And Lucas is currently a PhD student in robotics at the Université Paris-Saclay in Palaiseau and at ENSTA, the Institut Polytechnique de Paris, again in Palaiseau. And Luca will now talk about interval methods for optimal and guaranteed path planning. Luca, the floor is yours.
Thank you, Andreas, for the introduction, and thank you also for the invitation. It's a pleasure to be here today. As I said, I will present some works done during my first and a half year of PhD with my two supervisors, so Julien Alexandre Sandretto from ENSTA and Eric Lucet from CEA. And it's about interval methods for optimal and guaranteed path planning. So first of all, a bit of context. So my work is the part of French national challenge called Mobilex for autonomous mobility in complex environments. So it's co-funded by the French Defense Innovation Agency and the French National Research Agency. And it represents 7 French teams in France. And basically, the idea is to move heavy wheeled robots like cars, trucks, and rovers in complex environments. And so by complex environments, we think about little or no prior information about it, unstructured environments, hostile environments, problem of communication, problem of localization. So basically, everything goes wrong. And in this context, we need to move this robot. So it's differential robots. And so we need safety, we need guarantee. And so that's why in my PhD, I'm focused on path planning. And in this specific context, we can find in the literature a lot of approaches for path planning, but we want something guarantee, we want a path smooth, we want a lot of properties. We want to be able to consider uncertainties, nonlinear constraints, and so on. So we choose a specific approach that I will describe in this talk. So first of all, we choose B-spline curves as the support solution for our path. Why? Because B-spline are widely used for their smoothness and also for a lot of other properties, very interesting properties, and one of them is the local modification. So a B-spline curve can be locally modified, and this is very interesting, specifically in our context, because you can imagine a new obstacle discovered in the vicinity of the robot, and you need to avoid it, and so you need to be able to locally modify the curve. And we also want to use the interval arithmetics. Why? Because you want to be able to consider sensors uncertainties. We want to guarantee a solution which respects constraints. It's very important because constraints mean avoid obstacles in our case. And also, we want to use an interval branch and bound optimizer for the optimization. And why? Because interval branch and bound offer a lot of very interesting properties. And one of them is very important, is the fact that you can stop prematurely a branch and bound, and specifically an interval branch and bound, and you obtain a suboptimal solution, but you obtain a solution. If one solution was found in the past, of course, but you obtain one suboptimal solution. And this is really interesting because in our specific use case, we need to be able to guarantee that at a certain time, a path will be available and returned by the optimizer if the robot needs it. And so, in general, we need to apply this approach to extend B-splines to interval. Okay, because we need B-spline and we need to optimize the B-spline using an interval branch and bound. So we need to extend B-spline to interval. And so during in future slide, I will show you how we extend B-spline to interval. It's not something very simple because of the dependency problem. But first of all, before to switch to interval, I will talk you about non-interval B-splines, and just to explain how it works, how we build the B-spline, and some interesting properties. So basically, in this slide, you have everything to build a B-spline curve. And so first of all, the main element to build the B-splines is the basis. So here you have, we call them B-spline basis function. And basically, it's the n here on the slide. You have the equation here. It's a recurrence formula because it's easier to implement on a computer. And as you can see in the equation, you have multiple elements, ui plus p, ui plus p plus 1. These elements are a part of what we call the node vector, you see here. And the node vector is very important to build a B-spline curve because it will define a lot, it will influence the properties of the curve, and specifically the continuity property. And donc, so in the future slide, I will show you how the node vector can influence the types of the B-spline at the end. And so here I put an example of what we call a uniform node vector. Uniform, why? Because as you can see, the space between each element of the node vector is equal. So here it's 1. And if I use a node vector, I apply this equation, I obtain my basis of function that can build a B-spline. But I can also take a non-uniform node vector. And if I take a non-uniform node vector, I obtain a non-uniform basis of function. Okay? And here I put not a random non-uniform node vector, I put a specific one. And as you can see here, my B-spline is, my basis function, my basis is of degree 4. And if I put exactly 4, so 4 plus 1, so 5 times the first element in the node vector and 5 times the last element, I obtain the so-called clamped B-spline. And so a clamped B-spline is this B-spline exactly. So why is widely used is because specifically widely used in the computer aided design community. Why? Because as you can see here, the B-spline touch the first and last control point. And this is really interesting in a lot of applications because you can move and choose exactly the position where the curve will be. And so here you have the equation of a B-spline. Basically, it just consists of the sum of basis function weighted by control points. So here I have multiple control points, and with this control point, I can manage the shape of the curve. And this is really interesting because it's make the B-spline very powerful in a lot of application because it's defined by a finite number of control points, of course. Here I have the node vector that create this B-spline. You see that I have a B-spline of degree 3. So as I said before, I use 4 times the first element, 4 times the last element on the node vector, and I obtain this B-spline. And here I put a discretization of the parameter. So what is the parameter? The parameter is u here in the equation. We can see it also on the equation of the basis. And so the principle of the parameter is the parameter allows us just to plot the curve. And of course, we need to discretize it. And as you can see here, we discretize the parameter between elements of the node vector, between u3 and u4, u4 and u5, and so on. And this generates this B-spline. But here I choose a non-uniform node vector. I can also choose a uniform one. And so here, as you can see, the node vector is now uniform, and I obtain what we call an open B-spline. We call it open because it does not touch the first and last control point, but it's also called a uniform B-spline, of course. As you can see, the parameter discretization does not change. The equation, of course, does not change also. And we'll see in future slides that this uniform B-spline is very, very interesting, specifically in our use case, and you will see why. So yeah, B-spline curves are polynomial curves. So basically, you can change the degree of the polynomial. So here is the impact on the curve. You can also move control point. And as I said at the beginning, we have the property of local modification. So as you can see here, I move P3 and I only locally change the curve. It's not necessary to recompute the curve. In practice, when we move one control point, we will move a certain number of segments. So because B-spline curves are made from connection of segments, and each segment is a Bézier curve, so it's a generalization of Bézier curves. And when you move one control point, you will move a certain number of segments of the curve. And so, yeah, here I put the fact that the local modification is very useful for the optimization process because you do not need to recompute the entire curve. And the last slide about non-interval B-splines is just to show you the difference between non-rational B-splines, so the classic one that I presented to you just before, and the rational B-splines. So basically the difference is just that we introduce some weight here, you see, and this weight allows us to modify the attraction of control point. And if you modify the attraction of control point, of certain control point, you can represent more complex shape, like for example, this circle. And that's why rational B-spline equations are widely used by the computer aided design community for their ability to represent complex shape. In our application, we used non-rational B-splines because it's sufficient for our application and it's simpler to compute and it takes a lower time of computation time. So now we switch to interval. It's become interesting. So the first approach to extend B-spline to interval is to consider the control point as boxes. So as you can see here, it's no more a control point, but a box here also, and so on. And so I have this equation. So you see that here it's a box. Here it's not a box, it's a real number. And here at the end, I obtain a box. So it's a list of box. And this list of boxes represent my pseudo-interval extension, my pseudo-interval B-spline. And you can see the node vector does not change, and the parameter is still stays discretized and does not change also. This approach was proposed by the MIT in 1998. It's really, really interesting. Why? Because the only variable that appears multiple times in the equation is the parameter u here. And as here we we stay discretized, we keep a discretized parameter, we avoid totally the dependency problem because it's the only variable that appears multiple times in the equation. So with this approach, we avoid the dependency problem. And so this is really interesting in a lot of applications. And you have also a very interesting properties and a required property for the branch and bound is the inclusion. So if I take a control box, if I take, control boxes included in control boxes of another B-spline, I obtain a perfect inclusion like you see here in the animation. And this is a required property to use a branch and bound. But the problem with this approach, of course, is the discretization of the parameter. As the parameter is discretized, we define the discretization D like this. So it's the number of discretization of the parameter between two elements of the node vector. And so, as you can see, when we decrease the discretization, we obtain some space, some space between evaluation of the curve. And this is not suitable for class planning usage because we can imagine an obstacle just between two evaluation of the curve. And in this case, it's not possible to take into account these obstacles during the optimization process. And so we can collide these obstacles. So for our application, it's not suitable, but I think there are a lot of applications where you can use this extension. So what can we do more? Okay, the problem comes from the discretization of the parameter. So why do not take the parameter now in interval? So as you can see here, we still have a discretization, but it's an interval discretization. So here we keep the guarantee. We use IBEX for the implementation, so it's okay. And as you can see here, we obtain this kind of discretization for the parameter. The node vector does not change. Here you have an example of the natural form equation. So as you can see here, the parameter is an interval. So the basis is an interval. And at the end, the baseline will also be an interval, because the principle of this approach is to consider both the parameter as an interval and also the control point as control boxes, of course. And here I put an example of what looks like a basis function. So it's a polynomial. And here I just compute a basis function of degree 4. And so, yeah, I obtained this. It's just an example for this. When I made this slide, we used the classic form, so this form. But for now, we use the Horner form in order to reduce the natural dependency problem and also increase the speed of computation. But yeah, it's just to give you an example. And if I compute the basis, I obtain this. So here, what you see is exactly the same that I showed you at the beginning. It's a uniform interval basis of degree 3. So it's exactly the same than this. Okay, so it's exactly the same figure, but with the interval evaluation. So you probably understand that it's very complicated to use this basis to create a baseline. It's absolutely unusable, and you will obtain a baseline absolutely big, and it's not usable in practice. And so that's why the conclusion of that was the conclusion of IS in 2009. It say, okay, it's not possible to use interval to extend baselines. So it proposed something with the modal arithmetics. But in practice, for a long time, we have some approaches to reduce the dependency problem in the interval arithmetic. And one of these approach is to work with the form of the equation. And so we tried to use the centroid form and the Taylor form. So just to remind you, the centroid form, the principle is to evaluate the interval only on the derivative of the function, and the Taylor form, Taylor 1, if you prefer, is to evaluate the interval only on the second derivative. And using this principle, you drastically reduce the wrapping effect and the dependency effect. Why? Because the basis of the basis function of a baseline are locally highly monotonic. So when you compute the derivative, you obtain something quite constant, and so it drastically reduces the dependency problem. So we switch from this to this, so yeah, it's quite good. But what can we do more? It's to work on the variable. So before we work on the equation, and now we can work on the variable. And the second approach that we tried is to use the affine arithmetics. The principle of the affine arithmetics is to represent a variable by its middle plus a sum of what we call some noise number. And basically, the principle is that it drastically reduces the dependency, because when you will compute operation between affine forms, you will noise number will interact between them, and you will drastically reduce dependency. So if you compute x minus x, you obtain 0. It's not the case with the interval arithmetics. And so using this approach, as you can see here, we compute the basis using the affine arithmetics, and then we take the hull. So we switch to interval. We have also, of course, the inclusion. And if we plot this, you see that here we have the natural interval affine form. So it's equivalent to this, but you see that it's very nice, and it's better than the centroid form. So very interesting in practice, but of course it takes more time in terms of computation time. We also tried the centered interval affine and the Taylor interval affine, the same, but we compute using the affine arithmetics, and then we take the hull. And as you can see, for this discretization, we do not see any difference with the Taylor form. It's quite equivalent. So it's less, the affine arithmetics approach is less affected by the discretization, but it's more expensive in terms of computation times. So for now, I'll only talk about basis, but what about the interval B-spline at the end? And so here on this slide, I will compare different approaches that I showed you before and the result on the wrapping effect on the final B-spline. So here I started from the centered form because the natural form is unusable and is actually outside of the window. So started from the centered form, then the natural interval affine. So you see that it's quite better. The Taylor form is better, and you see that the centered form, the centered interval affine and the Taylor interval affine form are quite similar. Okay. But if I change the discretization, so here I take 23 instead of 50, and I obtain, you see that the centered form and the interval affine form growth. So you see the wrapping effect is bigger. And if I drastically reduce the discretization of the parameter, you see that the centered form and the natural interval affine form becomes unusable. So you can't use it. They are outside of the window here. And you see a difference between Taylor, the centered interval affine form, and Taylor interval affine. Okay, so quite interesting here. But what can we do more? As I said before, we compute, so I can come back here. We compute the basis using affine arithmetics, then we take the hull. What can we do is to compute the basis using the affine arithmetics, and then compute the final B-spline also using the affine arithmetics. And as you can see here, as the parameter u appear multiple times, of course, in the equation of the final B-spline, noise number will interact between them, and this will reduce the wrapping effect. And we just take the hull at the end of the computation. And if we do that, we obtain the yellow curve here, and you see that it's better than the Taylor interval affine. And just to give you an idea, I put here the pseudo interval in light gray, and you see that we are the Taylor affine and the pseudo interval approach are quite similar, but the Taylor affine is guaranteed. So yeah, this in our case it's good, but the problem with the Taylor affine approach is that it's complicated to use in an optimization process because we use an interval branch and bound, so we need interval to contract, to bisect, and here we have an affine form, and so it's complicated to bisect, to contract an affine form. So for the rest of presentation, I will take so everything that I will show is computed using the Taylor form. So the Taylor here in blue. Okay, so I present the theory behind the interval B-spline. So now we can switch to our path planner. So basically we use a classical principle called the generation over receding horizon. And the principle of generation over receding horizon is to take an horizon around the robot. So here, imagine you have a start point, a goal point, and an obstacle. So you take a planning horizon around the robot. You generate a solution over it. So this is draw by hand. It's not a B-spline. You generate a curve on this planning horizon, and then very important, you only save a part of this curve. Why you only save a part of this curve is to anticipate obstacle avoiding, because the next step is to move the receding horizon. And imagine that you move the receding horizon at the end of the first generation. You can imagine a situation where you have an obstacle, just like in my example, in fact, just be at the end of the generation, and the robot get blocked at the end because it can't move more without break the continuity of the curve. And so you need only to save a part of the generation and then move the receding horizon at the end of this part, and regenerate a path over the receding horizon, and so on, and continue like that until reach your target. So this is the principle of generation over receding horizon. And so how we do this with our interval B-spline. And so as I told you at the beginning of the presentation, we do not use non-uniform B-spline, we use uniform B-spline. And this is really important in this case, because uniform B-spline have a very interesting property. If you take exactly P is the degree of the curve. So here I have a curve of degree 3. So if I take 3 control points, and I reuse this control point to make another B-spline, I obtain a perfect connection between both without any more computation. So it's natural. And this is really interesting because uh, here you keep the continuity degree of the curve without any more computation. So you do not need to compute the first derivative, the second derivative, ensure that it's equal on the left and on the right of the connection. So here it's perfect by default. So very nice. And we use this principle to apply the principle of generation over receding horizon. So here I will show you so 4 slides about our optimization process. So basically, uh, in um, in a real interval branch and bound, everything is made in parallel. You made the contraction, then the bisection, then you evaluate the cost, you store the box, and so on. Here I will show you step by step how it works. So basically, you start with a random B-spline. You see that it's not smooth at all. It hits obstacles. So here we have circular obstacles and also box obstacles. The first step is to consider constraints. Okay. So our first constraint is to avoid obstacles, of course, is the most important. To do this, we ensure that each box of the curve is outside obstacles, outside with regarding to the natural interval extension of the distance. So the distance need to be greater than the radius of the circle, and here it's the distance to another box, so it's easy, greater than 0, and it's okay. The second constraint that we use is that the last point of the curve here must be close to the planning horizon. So as you can see here, it must be close. And to be close, we consider that the center of this last box need to be included in an interval around the planning horizon. Okay, so this is our constraints. We have 2 constraints, so it's okay. And for the optimization, we try to minimize the sum of distance between control points. Why we do this? Because we use a very interesting property of B-spline curves. A B-spline is included in the convex hull made by its control point. We call the convex hull, we call it the envelope. And so when you minimize the sum of distance between control point 2 by 2, you minimize the area of the envelope, and so you smooth the curve naturally. So we use this principle to smooth the curve. And then uh, uh, we minimize also the distance between the last point of the curve and the target. Why we do this? It's just to be sure that at the end of the movement, the robot reach the target. And yeah, I don't explain it, but we ensure that the last point of the curve must be close to the planning horizon. Why we do this? It's just because we want to be sure that the planner will progress spatially. Because if you do not do this, maybe the robot will stay at the start position. And so, yeah, sorry. Here, I just to give you the example, here I put an example of what could be a prematurely stop optimization. So as you can see, it's suboptimal. We have some wave. It's not smooth, very smooth. And if we do not consider time limit for the optimization. So the interval branchment will reach the required tolerance. We obtain something very nice, and it's exactly what we want. And so basically, we can play with this prematurely stopped optimization to obtain a solution if the robot need it very quickly. So now we switch to the application. So we implement everything in C++, standalone. We use IBEX for the computation of the arithmetics. We compute all our B-spline using SimEngine for symbolic computation. So everything is it's quite okay. And so our local planner is divided in three parts, three C++ objects. So the first one here on the top is the brain of the planner. Basically, you have here the feature management, you have the link to the middleware, and so on. Here you have the numerical constraint optimization problem management. So basically here we create our constraints, we create our cost function, we create the IBEX optimizer, we launch the optimization and so on. So everything is computed here. And finally, we have a C++ implementation of our interval B-spline that I show you the theory at the beginning. And so in this code, you have everything related to interval B-spline, so the computation of the basis using the natural centered Taylor form. You have also tools to evaluate the B-spline and so on. So everything is doing is this code. And so as you can see here, it creates a box, so it's our planner. And as inputs, we use the start point, of course, the goal point. So the start point corresponds to the position of the robot at the beginning of one optimization. So we can move the start point. It's the position of the robot. We have the goal point, and we have some parameters, of course, because we can choose the degree of the baseline, we can choose the time for the optimization, and so on. And we also have a list of boxes and circles that represent our obstacles. But we want something that works in real life, and in real life, you do not have boxes and circles as obstacles. You have some cost map from ROS, for example, 2 degrees, and so we developed a simple cost map converter. So basically, the principle is to cover obstacles with circles and boxes, and and return these boxes and circles to the local planner. And very quickly, just some approaches that we use to cover obstacles. So here on the top left, you have a very brute force approaches that does not work in reality. The principle is to put one circle per pixel of the contour of obstacles, or one box per pixel of contour of obstacles. And the problem with this approach is that we obtain a lot of constraints because each each box or each circle represents multiple constraints for our optimization process. So it's not very usable. So we try to reduce the number of circles with these two approaches here. But for now, we converge until to more simple approaches, like this one on the bottom of the slide. So here you have an approach. The principle is to put one circle per obstacles. Here, this approach is to put one box per obstacles, and this approach is an interval branch and contract. So in my opinion, it's the best one in our case, because it's a very good approximation of the cost map, and you can choose the size of atomic box. So it's very interesting in our case. And so very quickly, this is the implementation that we use. Very classic implementation. We have a global planner node, a local planner node, and a controller node. We use ROS2, so everything in red is related to the middleware, so ROS2, and everything in green is related to standalone C++. And so as you can see, we use an ENSTA as a global planner. Then we use our planner based on the interval methods that I presented before. And for the controller, we use an MPC at the end. And so here I will show you some simulations. So basically, first we start with a simple environment with a differential robot, differential wheeled robot. This is the Jackwell from ClearPath Robotics, if you want. And you need to avoid a cylinder. And you see it's an empty world in a gazebo. So it's a gazebo, it's an open source simulator in Rust. And it's just to show you the impact of the time limit that we give for the optimization. So as I said before, if you give more time for the optimization, you will obtain something more optimal, and you will see that it's quicker on the top of the slide, but the robot will reach the target first on the bottom of the slide. So if I start the video, you see that, yeah, it's quicker here, but it's more optimal here. And at the end, you see that the robot reach the target first with a time limit of 0.5 seconds. Okay, so now I switch to a more dense environment with more obstacles, as you can see here on the world. And here on the left, we have a time limit of 0.1 second. On the right, we have 0.5 seconds, and you will see the difference. It's very interesting to see. So here it's quicker, of course, but you see that it's very suboptimal. And here you see that the robot is able to pass through narrow passage because we give more time for the optimization. So yeah, it's better, it's more optimal, and it's in the robot, of course, reach the target first on the right. And as you can see here, I used a mix version between the strategy that use box and strategy that use circles to cover obstacles. So it's choose the one with the less the area with the best area covered. Okay, and now if I switch, so to finish this presentation, I switch to a real life experiment. So it's a proof of concept. It's a very simple environment, indoor environment. So we currently work to improve the code, of course, but it's just to give you an idea. Here, the covering of obstacles is made by an interval branch and contract. You see that we also inflate a bit boxes in order to consider uncertainties on obstacle, but it's not something precise. Just in order to be sure to cover the entire obstacles with this version of the code. And if I launch the video, you will see that the robots will avoid the obstacles and the planner generates the good path, avoiding obstacles. Okay. And yeah, you see some dynamical corridor here computed. It's not related to my planner. It's some corridor that we use because we use MPC, a special MPC that is constrained, and so it's constraint. The constraint of the MPC is to ensure that the footprint of the robot need to be inside the dynamic corridor. So this is interesting, but not the subject of this presentation. So to conclude, we developed first an application able to generate, optimize, and evaluate interval uniform, non-uniform, rational, non-rational B-spline curves. To reduce the wrapping effect, we tested both modifying the form of the equation, so natural centered Taylor, the form of the variable with the affine arithmetics, and we also developed a C++ and ROS2 implementation of a new local path planner using interval method and interval B-splines. And regarding our future works, we want to evaluate the full B-spline using the affine arithmetics and plot it using Zonotop. It can be interesting to see what will happen. Also evaluate the B-spline using the modal arithmetic to compare with regard to the paper that I showed you during the presentation. We want also to reduce the computation time, and so we'll try some approaches, like, for example, work on the contraction process. We want also to be able to include the cost map in the optimization in order to take into account, for example, the ground quality. This is really important in our use case. And also, we want to be able to add the curvature as a constraint, because for now it's not a constraint, and so we want to control the curvature in order to ensure that the robot can follow the path, because we do not use any kinematic or dynamic model. It's just a path, and all the points are not temporally linked. It's very important to say that. And also, we want to perform some outdoor tests to test everything on the real platform that I show you at the beginning of the presentation. So thank you for your attention. If you have any question, do not hesitate.
So many thanks, Luca, for your very interesting presentation, and I'm pretty sure there will be some questions. Who wants to start? Maybe let me start with one question related to your outlook. You mentioned at the end that you want to take, for example, also temporal information and also curvature information. I would say, in fact, this is turning your path planning then into something that we could also call trajectory planning.
Yeah.
If we are doing this a little bit more general, have you already thought about integrating something like using the B-spline curves that you have introduced here as a nonlinear time scaling within, for example, DNEBEX as a solver? Because if you do this, you could, for example, start with a linear dynamic system model that is very easy also to integrate in a guaranteed fashion. And
Yeah,
then,
yeah, very, very.
nonlinear time scaling would turn the ODE into something nonlinear. And then you could, in fact, do quite simple verification for specific class of nonlinear ODEs.
Yeah, yeah, you're right. Actually, for now, I do not think about temporary consideration because we used an MPC that does not need to consider temporal logic. It just take as input a path, and it allows us to, for example, just go forward or go backward without the requirement to recompute the curve. So for now, I do not consider the time, but you're right, it could be very interesting, and of course, using Dinibex at the end.
Yeah, and maybe if I can immediately continue, uh, what you're assuming at the moment in your MPC is, yeah, more or less that you know, yeah, due to those measurements, for example, of the obstacles, that you know more or less some guaranteed information about your environment. Have you thought about identifying also some further environmental properties? For example, include this strategy into a SLAM procedure and or similar?
Yeah, yeah, you're right. It's really a good point in my thesis because I'm focused on the planner for a guaranteed planner, but of course, if the perception is not guaranteed, it's not efficient. But I think it's very another subject. So for now, I'm focused on the planification, and I hope someone else will work on the perception. But yeah, you're right.
Okay, okay, that means you're starting now to write up a proposal for a second PhD project,
Exactly.
submit it to Julien, and he should try to find a second candidate who will be working on it.
Yes.
Yeah, that's great. Okay, any other questions? Maybe just a really stupid question. What is the target platform on which you want then at the end to run your C++ standalone code? Will this be some, let's say, low-cost devices, run it on Raspberry Pis, or do you need a larger computational power?
No, actually, it's a classic computer. I think on the robot that I here in the demonstration, it's an onboard computer, and it's a Ryzen 5, I think, as a
Okay,
CPU.
that means you even run it on board and you do
Yeah,
not
yeah,
need to
yeah.
transmit the data somewhere else, use a
No,
high-performance workstation or whatever and
no,
transmit the data
no. The
back. It's
principle is really
already.
to make something on board.
Mm, okay, that that's really nice.
Thank you.
Yeah, okay.
I have
Now,
one. I have one question.
yeah, please go ahead.
Thank you. I'm Brahim Brahmi, assistant professor from CAF UPM, Saudi Arabia. Thank you, Lucas, for this nice presentation. So my question, actually, I have two questions. The first one, the trajectory here is global or local. So your approach can solve or planner the motion for global path, for example. And the second one, we can use this approach, for example, for other kind of robot, like drone, for example, to avoid obstacles. So there is some 3D dimension. So it's can adapt this approach with 3D space or no?
Okay. Okay, so thank you for your question. Yeah, oh, basically what I'm doing is very at the beginning it was the idea was to create a local path planning. But at the end, what we see is that the optimization process and so the progression of the curve, as you can see on the video here, if I launch the video, sorry. As you can see here in the video, the generation of the path is not linked to the speed of the robot. And so, in a sense, we can imagine that if we optimized a lot the computation, you can obtain a kind of global planner, but it's start at, of course, at the position of the robot. But I think the transition from local and global in our case is just the question of the computation time. And so I hope it's answer your question. And
Yes, clear.
the,
Thank you so much, Lucas.
and
And for the second one?
yeah, and the second one, yeah, B-splines are very nice because it's very easy to use in 3D, in 4D, in 5D, in every dimension that you want, because you only have the basis is the same. You only have to take control point in a higher dimension, and you obtain a B-spline in higher dimension. So you can clearly imagine extend this planner to 3D to use in with drone or something else, but in my opinion, for now, the problem will be the computation time because you add a dimension, so it will increase the computation time. But in theory, it's okay.
Okay. Thank you so much, Lucas. Very nice presentation.
Thank you.
Okay, then it's again my task. Is there anyone else with a question? This doesn't seem to be the case. Then again, many thanks, Luca, for your presentation.
Thank you for the invitation.
And yeah, the remaining thing is I need to advertise for next week on Friday. We'll already have the next talk. Theo Le Terrier, who is also present here in the audience, will present next week. And yeah, we're also looking forward to this presentation. And until then, I wish all of you a nice remaining Friday afternoon, evening, and nice weekend. And see you again soon in one of the upcoming seminars.